Good morning, everyone. It's a pleasure to have so many of you on board. Today, we will have a webinar with the topic of fatigue properties of aluminum castings, the role of both visible and hidden damages. My name is Ehsan Qasem Ali. It's a pleasure to host you today for this webinar. It is a part of project that is called WebLearn that I will introduce soon, in which we have series of webinars every 2 weeks. And this is webinar number 28 in the WebLearn project under the module number 6, which is about non-ferrous metals. Today, we have more than 100 registrants for this webinar, which is a record for us, from more than 20 countries, and it's a real pleasure to have all of you with us, and I hope that you will also enjoy the webinar today. Very international as well. As I said, this webinar is a part of WebLearn project in which we conduct focused and in-depth webinars related to metal and polymer component manufacturing. It's a project that is supported by Knowledge Foundation or KK-stiftelsen in Sweden, in close collaboration with industry, related industry in Sweden, with the aim of reaching out to international audience as you. So every 2 weeks we have a webinar, and the project actually, externally funded project, will end by the end of this year. But the plan is to continue the activities because we see it as a very useful platform for dissemination of research results and getting closer to the stakeholders of the research we do. You see the moderators of the webinar today, myself and my colleague Anders, who will come in the panel discussion. You will hear more from Anders later on, but more importantly, we have the webinar presenters, Professor Murat Tuyaklu from School of Engineering Technology, Jacksonville University in Florida and USA, which we have the honor of hosting Murat right now at Jönköping University as a visiting international professor. And also Tony Bogdanov, who is at the Department of Materials Manufacturing, School of Engineering, Jönköping University. This is the agenda for today. The times are Central European Time. After this short introduction from myself, we will have the wonderful presentations from the presenters that I just introduced. And after that, around 11 o'clock, within almost 1 hour, we will have a panel discussion in order to go deeper into the topic and hopefully get your input as audience as well to have a more interactive webinar today. And we hope to wrap up the webinar within 1.5 hours from now. Some short technicalities. We would appreciate if you turn off your microphone during the webinar. Questions are more than welcome, but it would be great if you raise them in the chat during the presentation. You can either send it to everyone or send it to myself, Ehsan, and I will take care of asking them from the presenters when there's time for it. Otherwise, as I mentioned, there is a time for panel discussion at the end of the webinar where we would welcome your questions as well. So you can either raise it during that time, again in the chat, or unmute your microphone and raise your question yourself. Our webinars are all recorded and the recording will be available to you afterwards. So if you do not want your video or picture to be recorded, please turn off your camera during the presentations. What we will not share with the audience is the panel discussion. So in case you want to turn on your camera or microphone during the panel discussion, please feel free to do so because it's actually becoming easier for communication and discussion. And we will assure you that that part will not be shared afterwards. I think Due to pandemic, we all know how Zoom works, but in case somebody doesn't know, these are where you can find different items in Zoom, where you can mute and unmute your microphone, turn off or turn on your camera, and the chat function that you can find in a Zoom to raise your questions, as I mentioned, to myself or to everyone. That was from me, and I would like to hand it over to Murat. Please, the scene is yours.
Good morning, everyone. I hope you can hear me well. Thank you for attending this webinar. I would like to start thanking my colleagues here at Jönköping University for inviting me, hosting me, and making me feel at home. It has been a wonderful 6 weeks so far, and I have a few more weeks to go. I welcome everybody joining us internationally, and I would like to give a special shout out to my colleague at Jacksonville University, Dr. Paul Dinius, who woke up early at 4 a.m. to watch this webinar. I appreciate you, Paul. So today we're going to talk about the fatigue properties of aluminum castings with special attention given to the role of visible and hidden damage. I gave a webinar in December 2021, almost exactly 6 months ago, with the title Manage the Damage. If you have not seen it, I strongly recommend that you watch it. I think you can get the link from Ehsan. And we're going to build on that. But for those who have not watched that webinar, we're going to give some of the highlights from that, because this is more of a Manage the Damage part 2. And my partner in crime in this webinar is Tony Bogdanov. Let me start with a confession. I'm going to show you the boring stuff, and he's going to show you all the exciting videos. Okay, let's get to it. So the agenda is, again, we're going to have the Manage the Damage recap. What is damage, where it comes from, and we're going to give you a case study, strain concentrations in tension. Then we'll talk about how to quantify the damage, both visible and hidden. Another case study where we follow the damage at a foundry. We'll jump into fatigue properties of aluminum castings, how inactive oxides present themselves during fatigue testing. Another case study will follow. We'll talk about intermetallics and silicon particles. Then the effect of structural damage on the fatigue performance of cast aluminum alloys. And I'm going to finish with the environmental impact of low expectations. Damage in our castings, where does it come from? I took this picture about 6 months ago when I was walking on the beautiful Jacksonville beach. It's a fantastic beach. You should visit it if you've never been there. And what we see here is a lot of water. We see the Atlantic Ocean. And why am I showing you this picture? Because we see a substance that we are very familiar with. It's water. Our lives depend on it. We interact with it many, many times during the day. We take a shower in it. We use it for cooking. We drink it. We wash our hands. Our lives are intertwined with the use of water. So when it comes to water, we know how to treat it. But when it comes to surface the liquid aluminum, it's a different story, because the surface of water is covered with water, whereas the surface of liquid aluminum is covered by an oxide, which is a solid ceramic. And it's harmless as long as it stays on the surface, but when we start treating liquid aluminum as if it were water, then we run into problems. And it's here you see a very coarse aluminum oxide, and we usually disturb the surface, and this results in the folding of this oxide, and it's being entrained in the body of the liquid metal. Because the solid to solid oxide contact creates no bonding, we effectively introduce cracks into the liquid metal, and these cracks find themselves into the casting, and after that they serve as cracks which affect the performance of our castings. So the entrainment defect is what we call the biofilm, is the folding over of the liquid surface film. And in the process, we also have air bubbles, which leave behind oxide trails, and we're going to show some of them now. Here are some of the biofilms that were found in aluminum castings. On the left, you see one that is very crumbled, and just in the metallograph, it was cut through it. You can even see one half of the film over here presenting itself. There's another one that is completely folded, and most of the times these biofilms are invisible in X-rays. They become visible only when you look at the fracture surface. And when you zoom in into this area, you see that there is no bonding between the two sides of the biofilm. So it is definitely a crack. When we look at how we treat liquid aluminum in the production of aluminum castings, I found this video online, a YouTube video. So I would like to show a small section of it. We have the central melting furnace, and it's away from where the casting is produced. So the liquid metal has to be transported, and you see how liquid bubbles formed when it was being poured into this ladle. The ladle is taken away by a forklift. It's taken to the casting furnace, and it's going to be poured just like we're pouring water from a distance, and you're going to see all the violent mixing of bubbles in the crucible, the lower crucible in the casting furnace. And this is a very highly damaging process. A lot of oxide is being entrained into the liquid metal. And you'll see that it's going to take a while for the air bubbles to come through. So what do? We use bucket technology. So we fill the buckets with liquid aluminum, and we pour it just like we treat water. Because we know about water, we interact with water, and we treat liquid aluminum as if it were water. And we like them so much that we pour from one bucket to the other. So as long as we keep these buckets in our production systems, damage to our liquid metals will always be inherent in our castings. Just to show you what happens in these plunging jets, there's a technical term. It's well known in civil engineering literature that it's a perfect way to create a liquid and air mixture. We have a plunging jet here on the upper left-hand side, and it's hitting the surface of the water. And on the right-hand side, you see a more zoomed in version of the air being entrained into water. So everything you see here is air being entrained because there is a jet that's plunging into the surface of the liquid. And of course, if this were aluminum, it would entrain the surface oxide along with air. And when air is entrained, it of course floats up to the surface, but in the way it reacts with liquid aluminum and it leaves a bubble trail. So that's another oxide, that's another entrainment defect. And here you can see the top of the bubble. It's like a balloon, and you can see that it's like a string attached to the balloon that's left behind, the damage left behind by the air bubble. So these melt transfers, this bucket technology is very, very harmful to our castings. Then one more thing that we do, cleaning, I put 3 question marks because I am quite confident that it does nothing as far as cleaning is concerned. We use argon and then use flux. It's a violent reaction. You see the vortex, so you see the surface being entrained into the body of the liquid metal. And I think this is somewhat recent because degassing used to be much more quiescent, but recently this has become more and more common. So what we do with this approach is, perhaps some of you are familiar with the reduced pressure test, where we take a sample of aluminum and let it solidify under a reduced pressure. Then we chop it up and look inside, or weigh it and find the density. If we see no pores, we say, this is good, no problem, this is fantastic. But I have a different approach. Let me show you. If this is the density versus hydrogen content in the liquid metal, then if we have a very highly damaged melt, we would have a relationship like this. Obviously, increasing the hydrogen content would decrease the density of the RPT sample. But with decreasing damage, this line would get less of a slope. And with no damage, this would be a flat line. In the manage the damage presentation, I outlined, and I even gave examples from the literature of how much supersaturation of hydrogen is reported. It was 313 times above the solubility. Okay, so when we look at the data, for instance, we can immediately see that this is reflected in the data, the effect of the damage. So what we do by degassing is, if we have this kind of sensitivity to the hydrogen level, by bringing it down, we basically shut it off. So we take a broom, we sweep it under the rug, and we don't see it. We don't see the trash, it's under the rug, no porosity, no problem. That has been the approach. Unfortunately, by making the damage invisible, our problems do not disappear. In fact, they become increasingly worse. And this is what has motivated us to, again, bring your attention to this topic. So let's talk about visible and hidden damage. And what do I mean by hidden damage? Well, all of us are familiar with the visible damage, and those are the pores. We have been dealing with pores and battling pores in castings for a long time. Now, you're seeing a pore that was created by entraining some air, by pouring the metal from a height, and it was allowed to solidify in a reduced pressure test. So the pore was quite large. So we were looking at it, although our starting metal was of high quality with very low pre-existing damage. And when we were looking at it under the microscope, we noticed this curious feature that you see with the arrow. And what is that? So we zoomed in, and looked a little bit closer. And when we turned on the X-ray map, it clearly presented itself as an oxide. So there was a folded biofilm, folded oxide, hiding there. It did not open up, although we tried everything that we could to open everything up on the reduced pressure test. It did not open up. It remained folded. So we refer to those as inactive oxides. It's the hidden damage. Then we went to another place near this pore, and this looked like an interesting place. And when you look at it, there doesn't seem to be much other than the pore. The pore is always getting our attention. But again, turn on the X-ray map, and all of a sudden you see all these biofilms that are there that did not open up. They are just closed. They remain closed, although we did our best to open them up, they remain closed. So that is the invisible damage that we are referring to in today's webinar. And that's a little bit well known in certain circles. I came across this in the fatigue literature. There's the pore, and in fatigue, we would take this maybe as the initial fatigue crack initiating defect, but actually the extent of the damage is much larger. Here you see the interface, the biofilm with unbounded interface extending from the pore, and that's no wonder. In many studies, cracks were observed to start propagating from pores on the very first cycle. Okay, so yes, we can hide the damage, but there is one thing that the damage, the invisible damage, can never hide from, and that's a tensile stress. They cannot withstand the tensile stress. So here's an in situ tensile test. You see a pore, and at a very low stress, you see multiple cracks presenting themselves around the pore.
Yes.
Here's another one. And again, in this case, there's a silicon particle, but there are cracks in the structure. And these biofilms, the inactive oxides or the hidden damage, now starts presenting itself. It's no longer hidden because it cannot withstand the tensile stress. So the important concepts about damage that we want to emphasize are that pores are only the visible parts of the overall damage. The real damage is much more extensive. Closing the pores, such as with HIP or squeeze casting, they usually have very low return on investment. You can refer to the manage the damage presentation for examples. We are of the opinion that hydrogen is not a contaminant. Hydrogen cannot form pores without entrainment damage. Hydrogen makes the damage visible, and if you bring the hydrogen level down, all you're doing is hiding the damage. You're not making the metal better, you're just making the damage invisible. And the only thing that the invisible damage cannot hide from is a tensile stress. With this, we jump into case study one. Tony?
Yes, thank you so much. Now we'll look a little bit at work that is ongoing at the university together with Jakob Olofsson and us that is here in the room presenting. We are doing a test on die casting aluminium alloys that has been casted. And then we did X-ray on the sample where we didn't see any visible damage at all, in this case porosity. And then we used digital image correlation using match ID to actually follow in situ strain distribution with 2 cameras in this case. And what we see during the tensile test is that we have regions where we see a clear high strain concentration. That will actually be the final fracture place as well. So if we continue, we see that the strain concentration moves a little bit and it's a little bit bigger. And this is something that we will continue to investigate, but it's clear that we have something that is not a pore in this case, that makes the damage and makes the fracture in this region of the material. So we have a lot of samples of this, so that will be a future work and something that we will publish in a while.
Thank you, Tony. So how do we quantify this damage based on what we have learned so far? Because the damage, whether invisible or visible, cannot withstand any tensile stress, our approach is to have the tensile properties in the evaluation of the damage, how much damage we have in the form of a quality index. So here we have a former study of mine in which I took data from the aerospace and premium casting literature and just put it all on a graph. Here we have yield strength, which is minimally affected by the presence of defects. And here we have elongation on the y-axis, which is strongly affected by the presence of defects. And when we look at it, you'll see that there is a clear trend in the maximum points. And again, these all came from actual castings. These were coupons excised from real castings. These are not lab scale. These are not theoretical. This is not something that it was specially made. These come from production castings. So when we look at the trend of the maximum points, we can write an equation and we call it this ductility potential. And a simple best fit formula is 36 minus 0.064 times yield strength. This is in megapascal. So we can use this as a good point to estimate the potential ductility of our castings based on the yield strength. Okay, so let's then define the structural quality index. So if we have a data point, then obviously we have the elongation. But then we can calculate the maximum elongation that it would correspond to. And then we can define the quality index as elongation, the ratio of elongation to the ductility potential or the maximum elongation we have. So what this also implies is that this is, the remainder is the damage, is the loss due to the damage. If we had no damage, we would reach the potential. But because there's damage in the casting, we don't reach that. So this is also a measure of the damage. When we look at the overall regions, about 1.0, we don't have any data here yet. I think with more time, there'll be more data there. So the maximum trend line will shift, but for now we will use it. Between 0 and 0.25, we have highly damaged area. And most of our castings reside in that area. I would say 90 to 95% of our castings are highly damaged. 0.25 to 0.5 is moderate damage. 0.5 to 0.7 is low damage, and then 0.7 to 1 is very low damage. With that said, let's have another case study where we follow the damage. Tony?
Yes, and this is, we start in with how do we actually measure the quality. So what we have is, we have a lot of different techniques. And together with some colleagues of mine, we published a paper where we tested as many as possible. And if you want to read more about this, you can read this paper, it's published. But the finding is that tensile test is the most reliable test that gives result that we can trust. And now we also did the same, but we did it together with RPT and also tensile test to actually follow the damage in the casting process in a foundry. So what we know is that we have a melt furnace where we melt, and we saw that, and then we have to get the melt somehow to the transport ladle, and that is by pouring, and we do it like water. And when we look on the quality, and continue this one, we do this fantastic step of degassing that we can see in this video, where we actually see one more time this big vortex dragging the surface down into the melt and creating more damage. The next step is that we have to continue and pour it into the casting furnace, where we actually do another step of this one. You see a violent flow, just filling the furnace as fast as possible to actually get the melt into the furnace as in a short time as possible. So when we look on the quality in these different steps, we have to take care of that. This is an ordinary 46,000 alloy. When we do the RPT, we see that we have pores opening up. We have a yield strength of 128, elongation to failure 1.2. And if we look on the quality, we have 0.04, so we have a loss of 96%. Then we pour it one more time. We see that it doesn't change the properties to that extent at all. But then we have this fantastic step with the degassing, and wow, we have achieved fantastic density index. We have achieved a sample without porosity, we have some visible defects, but the properties are the same. So the loss to damage is still 96%. And then we pour it one more time. And what we see in this case is that all of this process that we have is actually not changing. We can see a small degradation in the properties, but we have a loss to damage about 96 to 97%. So the big question is it actually worth to actually do these steps when the quality of the melt are so low as it is from the beginning? So the damage of the melt transfer, it will not matter at all. The damage increase a little bit with each transfer. The degassing in this case, it's only hiding the damage with actually no real cleaning. Yes, it reduced the hydrogen level to a small extent, but what we can see from the mechanical properties and the tensile test, we don't see any difference. So is it worth to actually do these steps in a foundry with this quality of the melt from the beginning?
Thank you, Tony. So with all this in mind, let's come now to the fatigue properties, and let's bring all this knowledge into how this is affecting fatigue properties in castings and what the role of the damage is. Now, I'm going to start with a confession. I also belong to the long list of people who focused on pores, the pore sizes the way they are. And we know that when we look at the fatigue crack initiators, and if you plot them with the size on the x-axis and fatigue life on the y-axis, there is log paper. There's a trend line, and I focused on that. I published that, but now I know that that is not the complete truth. There's a whole lot more to it. But it's so easy to focus on the visible part of the damage. That's the pore. What if the pores don't exist? So we're going to talk about that today. Here are some recent examples of in situ fatigue testing. These are low cycle tests at high temperatures. here you see two pores, but at the first cycle, you're going to notice that a hidden biofilm opens up and presents itself. It's not at the point of the highest stress concentration. This crack opens up right away at the first cycle at a high temperature, where you would expect the metal to be very ductile and absorb this kind of energy, but it doesn't. It opens up. And then after a few cycles, it's lit to the main pore. Many other biofilms open, all the way from very small to large. And all the crack has to do is to follow those opened up damage to cause the final fracture. So if you don't see this in real time, and when you look at the fatigue specimen, you say, oh, okay, this is fatigue damage. But actually, the fatigue crack is following the transfer damage, the liquid metal damage that was created during processing. So that is the main thing. What has been usually referred to as fatigue damage is in fact damage given during the processing of the liquid. I'm going to show another study, again, similar. This is, I think, 319 alloy, automotive alloy. And these were excised from engine cylinders, cylinder heads. So actual castings. So 10 cycles. And then there are two pores, and at a point in the middle of the pores, there's a strain concentration, just like what we showed you earlier in case study 1 in our tensile test. You don't see anything there, but all of a sudden there's a strain concentration, knowing that there was a hidden damage there and it's now opening up. And a few cycles later, everything else is opening up. So many small biofilms are opening up. That large area has opened up completely. It turns out it's a quite large biofilm. And again, all that needs to happen for the fatigue is the linking of these liquid metal damage. And then obviously it's a very energy efficient process for a fatigue crack to go through these opened up biofilms during the fatigue cycle. So fatigue propagation in general in these alloys, in aluminum plastics, they usually starts on the first cycle, immediately after the first tensile stress cycle, from the pores. Why? Because we know that there is hidden damage around the pores. We've seen it. The crack propagation path follows the cracks that open up in front of the main crack. The secondary cracks around the pores, no pores, silicon particles and intermetallics. We're going to talk about them. They are quite strong. Let me give you a heads up. They should not crack like that. And in high cycle fatigue at room temperature, there are large flat areas on the fracture surfaces where we don't see any beach marks. All we've learned when we were taking the first lesson in fatigue, how we see beach marks on the propagating crack, and all of a sudden we don't see those. And here's an example, large areas that are completely free from beach marks. Cleavage, a lot of cleavage going on. Okay, this brings us to the next case study. Tony.
Yes, thank you. Now we will talk about a casting in aluminium, a 42,000 alloy that we casted in a staircase casting. We tested it in the as cast condition, And what we did later was, because we know that we should have porosity in this, we did hot isostatic pressing, hipping to the parts that we machined, and also we did a T6 heat treatment of the material. And to actually validate that we are closing all the porosities, we are doing a CT scanning of the material. So the blue one is in the as-cast condition, and then the red one is after the HIP process, and green is done after the heat treatment after the HIP process, just to validate that no pores are opening up. But what is clear is that it's no pores at all after the hot isostatic pressing. And if we look on the microstructure in the as-cast condition, we see clear pores, and we also see a lot of hidden damage around pores in the other place of the material that we can see with the red arrows. We can find them in different places. And if we look on the HIPed and heat-treated materials, we also can find some part that actually has some damage that we can visibly see with our optical microscope in this case. Then we do the tensile test, just to validate what is the properties. So we have the as-cast that has up to 6% elongation. We have a quality index of this one between 0.07 to 0.16. So it's a loss of damage between 84 to 93, depending on that. And that is a lot of porosity in this one. But one of the interesting part is when we apply HIP and T6 and we look on the same properties, the loss to damage is 91 to 96%. So we are closing the pores, we make the material stronger, we get the matrix stronger, and we actually, in this case, opening up more defects in the material when we apply tensile stress to this one. What we saw with this one is that we are using a lot, I have been using a lot, this in situ cyclic testing that we can do here. We have a small stage that we can produce CT samples that we put in our SEM. So we can follow, and this technique gives us a possibility to actually see. This is the field of view that we can see that is on the A image in this case. So this is what we can see during the start of the fatigue test. What we can add to this one is a lot of extra information. We can do apply EBSD to get the grain size, so we can actually see if the grain size are having any influence at all. We can also follow the crack propagation in real time. And in this case, we can actually see in front of the crack that something is happening. All this small pattern is pattern made by the fib, so we can actually follow the strain concentration. So in this case, we are also using match ID to actually see where is the strain concentration highest. So if we link all this data together, we can actually investigate what is happening in front of the crack in this case. So what we see here is that we had a clear crack, that something is opening up in front of that one. So if we look, and then we can also take a video of this. So we can actually see it after with a video to see. So to the left of the notch, we see that this is the main crack, but we also see a lot of other cracks opening up. That one I will discuss more in the next case that we will discuss. But in this sample that was HIPed that we have, so we did the cyclic testing, and we saw after 300 cycles, we didn't see anything close to the notch where the strain concentration should be highest. But far away from the notch, we see things opening up in the material. So if we continue to the next picture, we actually see after 500 cycles that we have a lot of things opening up in the microstructure. However, nothing in the notch region where the strain concentration should be highest. So after failure of this sample, we investigated a fracture surface with EDS measurement and find different locations. And what we can find is that we have this brittle cleavage. We have some that is clear oxides and some that is intermetallic, that is expected. So we see that in the fracture surface and the fracture path, the oxides opening up are oxide films in this case, linking the fracture to the final failure. This is another example of an A35 alloy that we did on the same. And what we see before we start the video is that we have cracks far down in the red ring. We still have the notch that we can follow the propagation. And we see that we have an area in between that is not at all cracked, but we still see that the crack below is growing more and more, and then the crack is propagating in the ductile aluminium area that withstands the propagation until it finally linked together with the oxide crack in front that we can see on the right now. It continues to crack until the matrix is deformed to it has a final failure. So we see that this pre-crack that is in front of the highest strain concentration will link together and create the crack path in this case.
Thank you, Tony. So we have seen some intermetallics, silicon particles, and if you look at the literature, it's full of statements about weak intermetallics, weak silicon particles. So our question is, are they really weak or are they extrinsically weakened? So let's start with beta platelets. These are can be large particles. Some people refer to as needles, but they are in fact platelets. In most examples, not all, but you can clearly see a crack right through them, or they are split. And if we continue, they can be around pores, and they are known to affect the feeding of the liquid metal around the pore, but they can be associated with pores. But there are usually, they usually have cracks right in the middle. And I'm going to show you one more. Here is on the upper left side, you see a completely cracked beta platelet, and right next to it are cracked silicon particles. And we're going to see that there are also sludge particles that are cracked. The cracks are not only in the particles, but also in the aluminum matrix. What's fascinating about these cracks is that there's no tensile stress. Nothing has been applied to these. These were allowed to sediment to the bottom during the casting process, and they just opened up. It's opening up because these particles have precipitated on existing biofilms. So they are cracked to start with. The cracks are not happening because of a tensile stress. We see the crack because of a tensile stress in fatigue failure, but even in this example, there is absolutely no tensile stress, and we can see how damaged the metal is. So if you look at the aluminum iron intermetallics, there are some molecular dynamic studies that show that the ideal strength of these particles is between 14 and 19 gigapascal, way higher than we think they are. They are not weak, they are pretty strong. And they should have about 14% elongation in tension. So they are not brittle either. They can be very ductile. They are strong and ductile. So the only reason why we see them cracked is not because they are weak, but because they are extrinsically weakened by the invisible damage. Another example, I've already shown you the silicon particles broken. Here's another example. This comes from a fatigue paper. The silicon particles broken ahead of the crack tip inside the plastic zone, reads the figure caption. And the authors estimated the silicon particle strength to be about 160 megapascal based on fracture mechanics. Okay, sound calculations. But our question is, are they intrinsically weak or extrinsically weakened? And again, why do same cracks go into the ductile matrix? If these are weak and brittle, why is the ductile matrix not able to absorb that kind of strain? So when we look at, yes, the molecular dynamics studies, it's going to be exactly the same numbers as the iron particles. But there's a very interesting study that I would like to show you. And this is done by Müller et al. And where they found these silicon particles and they exposed them, and then they machined these notches, micro machined these notches, and then they ran in situ tests, and they measured the strength of these particles. Very, very interesting study. And what they found is the maximum strength they recorded is about 16 gigapascal, which corresponds perfectly with the molecular dynamic studies, which reported 16 gigapascal and about 30% elongation. Yes, in certain instances, they were weakened extrinsically, but the strength went down to about 2 gigapascal. Maybe there was an interface or there was a pinhole in them, but it never went to 160 megapascal. So again, we reached the same conclusion. Silicon particles are strong, but some of them are extrinsically weakened because there's a bifilm going through right in the middle. Okay, case study. Tony.
Yes. Now we will look a little bit about another experiment that we conducted with aluminium 7 silicon alloy with 3% copper. When we looked on the mechanical properties, we actually reached like a quality index of 0.6 with only 40% loss in damage in this material. We casted fingers and then we remelted the material in a Bridgman setup in a furnace where we actually can control the properties and produce material with low amount of defects. But what we did, we used the same in situ cyclic test, and what we can see now when we have like between 900 and 1000 cycles, we see a lot of secondary cracks appearing away from the notch. And this was something that we felt like, why is this happening? How can we investigate this? So we have a lot of cracks that we see, and they crack the copper faces, they follow everything. Are they always following the dendrite tips or in the dendritic areas? So what we did an interrupted test where we actually let the crack propagate for a while. And then we decided to stop it. So we actually can do an interrupted test. And then we used our SEM to do a fib sections. If you take the next slide. So we did a test and then we decided one area that we should investigate what is happening in front of the propagating crack. So what we do is that we fib the area around and then we can slice and polish and take pictures so we get every slice so we can see what is happening in front of the crack. So this is the first section and that is the last section, and then we can color everything. So in this case, we see this 250 slice. We have the crack from the beginning, and then we see all of this red. That is the crack that is everywhere in front. Now we add all the intermetallic faces that we have that show that when we go in, sometimes they are linked to the intermetallics, but often they are extremely not linked. So this is actually something opening up in the matrix of the material. That is clear that it's the hidden damage in this material. Really clear what we can do and see when we look what is happening in front of the crack. And that is something that we have discussed in this presentation a lot. But this is a clear evidence that we have oxide defects in front of the propagating crack.
To me, that's a fascinating result. That clearly validates everything we've been saying, and the fatigue performance is clearly covered by the invisible damage, and that's why we don't see these beach marks. We see all this cleavage going on in front of the fatigue crack. So, okay, let's try to bring everything together. What is the effect of structural damage on the fatigue performance of cast aluminum alloys? I've been thinking about that for a number of years, and this started when I got a phone call from one of my former PhD students, where he looked at the tensile properties in A206, then he looked at the fatigue properties. The fatigue results came later, and he called me and said, I could, everything we saw in tension, I could replace the word tensile with fatigue, and we're seeing the same things. So it dawned on me, okay, there's clearly a correlation. And I took those data later, and that's what we're seeing now. 3 distributions, vsible distributions that we saw. These are from the vsible distributions for the quality index versus vsible distributions of the fatigue life that we saw. So when I plotted the average versus average, the average quality index versus average fatigue life, I saw a trend that clearly linked the effect of the quality index or the damage, reduced damage, to fatigue life. And we can clearly see that if we extrapolate that to 1, which is basically free or very, very low damage, then, and if we are here about 10% quality index or 90% loss to damage, then we can clearly see we can improve the fatigue life by 2 to 3 orders of magnitude. That was huge. But I had only 3 data points. So I asked a master's student to look into the aerospace literature, and we did the same thing. These are coupons excised from real aerospace castings tested in fatigue. These are a little bit different geometry or flat specimens, but the link is clearly there. The link between fatigue life and log of fatigue life and the quality index or damage. So then we said, okay, can we also look at the automotive literature? Would that also apply to automotive literature? And the automotive alloy 319, very forgiving alloy. And we saw the same thing. We saw exactly the same thing, more data now, but the trend is there. The only issue was that we were stopping at about 25%, 0.25 quality index, or 75% damage. So is there a way maybe we can include more data points and see the overall picture? And the answer was yes. So we expanded the data sets that we used. But this question, the question I had since I graduated from my undergraduate mechanical engineering, why is elongation a requirement in castings? Because we never deformed them plastically. Why is elongation needed? It took me about 25 years to answer that question. And the requirement, the elongation requirement, is basically a de facto fatigue performance requirement. A fatigue performance requirement. And finally, I answered that question. I hope you agree with me. We can discuss more in a few minutes. Okay, so we looked at the Basquin equation. Everybody's usually familiar with this equation who is in fatigue, where this is the Basquin exponent. In physics literature, it was written that the physical meaning of the exponent is that it's a measure of degradation taking place at the micro level. So can it be related to damage? And the answer was yes. And here's what we found. We published this about 5 years ago. Here's the quality index, and here's B. And you can clearly see that, yes, there's a large scatter at the beginning, but the trend is very clear. And then the other, the strength coefficient of the Basquin exponent is also changing linearly with the quality index or loss to damage. So with that, well, can we predict the entire SN curve? And the answer was yes, more or less. We could estimate a little bit underestimates for the SCAST 319. The estimate is better for the underaged and overaged alloy. And here the estimate is pretty good. At a certain point, it's supposed to make a bend, but we did not expand it that far. So this is where we stopped. Obviously, it can be further developed. So here's now my case study, knowing what we know now. And how can we bring this to our expectations from castings? So what is the environmental impact of low expectations? Because I heard this argument several times. Primary aluminum has a large carbon footprint, so it is good for the environment to use secondary aluminum. And I'm not against that. That's perfectly a good argument. But then we turn around and say, because we use secondary aluminum, we cannot expect high properties from our castings. Okay. What is the penalty for that? That's what I'm focusing on now. So I'm thinking of a generic car. A generic car. It's not electric. My background in sustainability is not that deep, but I made a back of the envelope calculation that I would like to share with you just to initiate some thought, some discussion. Maybe someone with more expertise can take this deeper. But this car has a weight of 2 tons and an expected life of about 200,000 kilometers. It has about 150 kilograms of die-cast aluminum in the body. And the specifications, I think I'm right in these. The yield strength has to be 100 megapascal or more, and the elongation has to be 1% or higher. Okay. I'm assuming that the cast components are designed for fatigue. There's a design strength. That would mean that there has to be a design strength that goes into the design of the component. And there's a factor of safety. I'm assuming the factor of safety remains the same. So what is the environmental impact of over-designing the casting so that it does not break by fatigue and service? That is the question I'm trying to answer. So the data I use this 95 grams of carbon dioxide per kilometer. I think that's the standard. Everything has to be lower than that. But I'm going to use that number for simplicity. The yield strength is obviously 100 megapascal. If it's higher, that's okay. But I'm going to use 100 megapascal. The carbon footprint for aluminum, the latest numbers I found from the Aluminum Association is that primary aluminum has 8.45 kilograms of carbon dioxide per kilogram of aluminum, and secondary aluminum has half a kilo of carbon dioxide per 1 kilogram of aluminum. So we're going to estimate the SN curves from this simple model that we developed, and we're going to apply it to this thought experiment. So here we have some SN curves. We start with 1%. This is our SN curve up to 1 million cycles. And what if we increase our expectation to 3%? What if 5%? What if 10%? What does that mean? Here we are looking at a quality index of 0.034, which means 96% loss to damage. We think that that's okay in our castings right now. What if we say only, I will tolerate only 66% or anything in between, anything in between. So I'm assuming that we can take this fatigue strength, and from the fatigue strength, we can use it somehow a design strength. And that means I can take this fatigue strength. Now, the exact amount, exact number of the fatigue strength is not important because I'm using ratios. And I think the ratios will be close, so I have some confidence in these numbers. So if you look at the normalized design strength with changing minimum elongation value, we can see this. So if we go up from 1% to, let's say, 5%, the design value goes up about 60%. If we go to 10%, it goes up from 1 to 2.5. We can dramatically increase the design strength that we use for our aluminum castings. So what does that mean? The weight reduction potential goes up. When the design strength goes up, the part can be smaller, so the weight reduction potential goes up. This is only in percentage. It can go up to 60% if we increase our minimum elongation requirement from 1 to 10. Okay. Then, carbon dioxide not released per car. This is after 200,000 kilometers. Because the car is now lighter, it's no longer 2 tons, maybe it's 1,900 kilograms. It produces less carbon dioxide with everything else the same. So I plotted that. Then, yeah. So you can see that we can go up to about, I would say 800 kilograms of carbon dioxide not released just by increasing our expectation from castings. Then there is also some environmental impact because we are no longer using that much casting. And so there's some production carbon dioxide that's saved. That's 100% primary. That's 50% primary and 50% secondary. And if you add them together, this is the main savings. Total carbon dioxide savings due to higher elongation requirement. So then if you look at the car production, this is the curve for 50,000 cars. Now we're talking about kilotons of carbon dioxide. And if this is for 100,000 cars. So we're talking about maybe 80 kilotons of carbon dioxide not going into the environment because we have higher expectations from our castings. So in conclusions, pores are only the visible part of the damage. The total damage is much more extensive. Invisible damage cannot hide from the tensile stress. Bifilms open up during tensile tests and fatigue. The fatigue of cast aluminum components is clearly dominated by the damage given to the metal when it's in liquid state. We still treat the liquid aluminum as if it were water, and that has to change. Fatigue cracks initiate early from pores and or invisible damage. Propagation is basically linking of the previous liquid metal damage so that there is cleavage and no beach marks. We don't really see much of a fatigue during the fatigue of aluminum, cast aluminum alloys. Elongation requirement is a de facto fatigue performance requirement. The SN curves and fatigue lag can be estimated from tensile tests. And expecting too little from our aluminum castings, just because we treat them as if they were water, prevents additional potential reduction in carbon dioxide emissions. I think it's time, we think it's time to develop production techniques that create minimal damage to aluminum castings because our world deserves it. Thank you for attending. We sincerely appreciate it.
Thank you very much, Morad and Tony, for really interesting presentations and good insights to aluminum casting. Now it's time to move to the panel discussion. But if you agree, we had a couple of questions in the chat that I would read it for you